Okay, this is a chase problem that we began in class solving in small groups, but didn't quite get finished in the one class. So I'm gonna make a video of it and you can revisit it. So we see here that Kimi Räikkönen's driving a car, a Ferrari race car, and he leaves the pit with an acceleration of 6 meters per second squared. After 4 seconds, he enters the raceway. And at that same instant he enters the raceway, another car driven by Lewis Hamilton is traveling at a constant speed of 70 meters per second, and it overtakes and passes the Ferrari. If Kimi maintains his acceleration, how much time after entering the speedway, that's important, I've boxed those, is required, how much time is required for him to catch Lewis? So we want to draw a motion diagram, do some graphs, and then we're going to solve. So here's my motion diagram for Kimi. So Kimi starts here, and he's at rest, right? So there, his velocity is 0. And he accelerates, so we show acceleration by ever-increasing spaces in our motion diagrams. All right, that's probably far enough. Now, 4 seconds later, and if whatever dot we want to make 4 seconds, that's when Lewis is at the same place he is. So Lewis is here. I can make Lewis in red. Now, whoop, we lost some focus there. Lewis is traveling faster than the thing is there. So he's got to get there in 1, 2, 3, 4 dots also. So right about there, right about there. Should be evenly spaced. Yep, not quite perfect, but close enough where the red dots should be evenly spaced, indicating a constant speed, and the gray dots are ever increasing. But what we have that's important is at this moment in time, I'm going to call that T1. They're at the same place. And at this moment in time, I'm going to call that T2. They're at the same place. This is also the same place. I'm going to call that X1. And I'm going to call this X2. Just to keep things straight in order. And I want to find this time, right? This delta T. That's what I'm looking for. All right. What else do we know about these? We know Lewis's velocities here are 70 the whole time. We don't know Kimi's velocity of Kimi right there. Not sure what that is. Over here, we know Lewis's is 70. This velocity of Kimi final, we don't know that either. Oh, not 0, question mark. So does this make sense? Here, Kimi starts at rest, increases. When the time here is 4, if this time equals 0, this time equals 4. So at 4 seconds, they meet. And then sometime later, they meet again. Kimi accelerates, Lewis moves steadily. How will it this look on a position graph? So X, T. Now, I'm going to make my origin here. This will be X1. That's right here. It's because they're at the same place at the same time. Kimi is moving at a steady rate, so he's going to have a constant velocity or a constant slope. Lewis is, nope, that's not Kimi. This is Lewis, I'm sorry. This is Lewis. Steady. Kimi has a velocity, and so it's not, his slope isn't 0, but he's got a curved line, and they cross here at this. This is my time 2, and this is my x2. Now the slope is not 0 there. How does the velocity graph look? So Kimi has a constant velocity of, say, 70. We know it's 70. Did I say Kimi again? That's Lewis. I keep screwing them up. That's Lewis as a constant velocity. Kimi's is increasing, but begins, it's not 0, right? I'm doing it from here. I'm doing T1. T1. Graphing from T1. Looks like that. Here they have the same speed, but I don't really want to know that. So these graphs should make sense to us, hopefully. Lewis, which is the red line, constant slope of a position graph because constant speed, velocity. Kimi is an increasing slope, a concave up line. They intersect at 2 places, the pit and then later. The velocity, Lewis is constant. Kimi has some velocity at T1. My origin is this T1. And then steadily increases. Now this is the interval I really want to look at. This is the interval I have the most information of, and this is the interval where they correspond. The issue is, I don't know a lot about Kimi here. So if I list what I know about Kimi, the K list, right? What do I got for Kimi? Let me zoom out so I can show all that. Velocity initial, the velocity at 1, I don't know that. The velocity at 2, I don't know that. Position at 1, well, I'm going to make that 0. I'm going to make that 0. The position at 2, I don't know that. The acceleration during that time phase is 6 meters per second squared. And the time, that change in time, I don't know. What is that change in time? That's what I'm trying to find. I do want to find this. So I got to keep that. What about Lewis for that time interval? His velocity at the beginning, his velocity 1 is 70. His velocity at 2 is 70. His position at 1. So these are all Lewis's, right? Maybe put little L's, little K's for Kimi. His position is 0, same place. His position at the end is not known, but it's the same. That's really important. When you have things that are the same in 2 different parts of a problem or 2 different things that are moving, that's valuable information. His acceleration is 0, and his change in time, we want to find that also, and that happens to be the same as this one. Okay, so what do we do here? Well, we want to find the time, so we got to keep that. They have the same position at the end, so that's valuable. I want to keep that. I don't know these two, the initial velocity of Kimi or the final velocity of Kimi. But this initial, I think I could figure out, because I know he starts at rest and accelerates for 4 seconds. So what is his velocity, Kimi, at position 1? So the velocity of Kimi at position 1 is equal to the velocity of Kimi at position 0 plus the acceleration of Kimi times the change in time. Well, his velocity at the beginning here is 0. His
starts from rest. His acceleration during this phase is 6. And the time there is 4. So we now know that the velocity of Kimi at position 1 is 24 meters per second. So I can put that in here. Now it's important that we compare these time intervals that have the same displacement, because that's the time we want to find, and that's where we have a lot of information that agrees. Now, well, when we have these things, these pursuit problems or chase problems, we know their displacement or their position. We know their final position has to be the same. So we're going to use that. We're going to use that x final for Kimi is equal to x final for Lewis. That's what we're going to use. So I need expressions for x. So I need, for Kimi, it'd be nice to have, I want to keep the time because it's the same. Keep the final position because it's the same. This final velocity here, I want to avoid that. Avoid that. So I need the equation that does not have velocity final in it. And that equation is the x final equals x initial plus v initial t delta t plus 1/2 a delta t squared. Alright. We're going to move down here. So I'm going to use that. So what is it for Kimi? For Kimi, right, I want x of Kimi equal x of Lewis. Well, the x of Kimi is the initial of Kimi plus the velocity at 1 for Kimi times the time interval plus 1/2 the acceleration of Kimi times the time interval squared. That's my equation for the position of Kimi. I'm going to set that equal to the position of Lewis. For Lewis, I can use this same equation, but I'm using Lewis's numbers. I need x initial, which is x1 of Lewis, plus velocity 1 of Lewis times the time, plus 1/2 the acceleration of Lewis times the change in time squared. Now, you might know that since Lewis does not accelerate, I didn't need to use that whole equation, because this acceleration is 0, it's going to cancel out. But we'll see that when I put in the numbers here. So now I'm going to put in the numbers. 0 equal, whoop, isn't equals, it's a plus. 0 plus 24 delta t plus 1/2 of 6 delta t squared equals 0 plus 70 delta t plus 1/2 of 0 delta t squared. Because Lewis's acceleration 0, that blows up, that goes away, that goes away. So I've got 24 delta t plus 3 delta t squared equals 70 delta t, and that's, we can solve that for t and we have our answer, the time it took Kimi to find Lewis. I'll leave that to you, but that's how you set it up. When you have these pursuit problems, we have to realize that there's a time frame that's equal, or a time position, there's a time that's equal, and there's a position that's equal when they catch. And we use that information to set equal two equations and solve for one of the missing variables. Another way to think of this is, if you have two unknowns here, we need two equations. We do have two unknowns, the position at the end and the time at the interval. So we need two equations. We need an equation for Kimi, that's over here, and we need an equation for Lewis. I'll put that over here. And then we can solve. I solve them by setting them equal to each other. You could solve them with substitution. There's a number of other ways to solve those problems. Hope that helped.